Hello everyone and welcome to today's webinar, Adventures in Crowdsourcing Traffic Signal Applications, the fifth webinar in the EDC5 Crowdsourcing webinar series. My name is Neelu Parvinashtiani and I'll help with facilitating today's webinar. This webinar is sponsored by the Federal Highway Administration and hosted by the National Operations Center of Excellence, or NOCO. As a quick reminder, if you don't check our website and our resources through the useful links box that you see on your screen right now. We have also included 3 web links to the EDC5 crowdsourcing sites, previous webinar recordings, and also the upcoming webinars in this series. And we'll talk more about that during this webinar today. You'll see a box called download box, and in there you'll see the PDF of all the presentations from today, as well as a flyer on the EDC5 crowdsourcing workshops. So the other thing I wanted to mention on the logistics was that this webinar is being recorded, and that recording, along with the slides, will be shared on NOCO website on the on-demand learning section of the website, as well as on the page we created dedicated to archiving webinar recordings for this series. All the attendee phones are on listen-only mode by default, but we do love to hear from you with any questions or comments that you have during the webinar, so please type those in the question discussion pod that you see on the bottom right side of your screen. At the end of the session, we'll have a Q&A part for the webinar, and each of your questions will be read by the moderator and will be answered by the presenters. So that's all I wanted to cover, and with that, I would like to hand it over to our moderator for today, Greg Jones. Greg, take it away.
Oh, thank you very much. So again, as Neelu had alluded, we are going to have a webinar on adventures in crowdsourcing, specifically crowdsourcing for traffic signals. And today's presenters, myself, I work for Federal Highway's Office of Operations. My name is Greg Jones, and I'm part of the national team for the Everyday Counts 5 Crowdsourcing for Operations team. We'll also have a presentation from Jared Wall from Austin, Texas Transportation Department. He's going to talk to us about crowdsourcing applications in the Austin signal operations. Then we'll have 2 presenters from Washington, D.C., Rahul Jain and Tom Knopf-Chinsky. Rahul's with the District of Columbia DOT, and Tom is with Mead and Hunt. And they're going to talk about measuring road performance in the Washington, D.C. area. And then our 3rd presentation will be from Justin Effinger. Justin works in Illinois at the Lake County Division of Transportation. He's going to talk to us about integrating crowdsourced data into automated traffic signal performance measures. So I'll just briefly talk about Everyday Counts and our initiative on crowdsourcing for operations. The goal for this initiative is to increase the number of agencies that use crowdsourcing to better operate the transportation system through new and cost-effective and proactive operational strategies and applications. We identified this as an area of priority for operations, and over 30 states are pursuing this initiative through the Everyday Counts program. Some of the resources that we provide through this initiative, as Neelu mentioned, this is the 5th of the webinar series, Adventures in Crowdsourcing. We do have 2 more that are scheduled. Data for the back of queue applications, that's back of queue on freeways, and then also crowdsource social media data. So those will be upcoming in the future. We also do provide workshops, and as Nilo had mentioned, you'll be able to download a flyer if you would like to find out more information about how you could put on a workshop. And it's available to state and regional agencies, and it's somewhat customizable for the specific applications that you would be looking at in your area. We also do peer exchanges, and we have 2 of those coming up. The first one would be on real-time vehicle probe data, and then the next will be on use of free crowdsourced data. And then finally, we also offer on-site technical assistance, and this helps bridge technical, policy, or process gaps you may have in your state or local area for implementation of crowdsourced data. So there are 2 ways to receive funds that work with the EDC5 program. Each state has a state transportation Innovation Council, better known as the STIC, and there's a incentive program that's available in each of the states for up to $100,000 per year for that Innovation Council to be able to standardize an innovation in the way that they best see fit within that individual state. And secondly, there's also the Accelerated Innovation Deployment Demonstration Program, and each year up to $1 million is available to deploy on innovations that are not routinely used. Now, that's not necessarily $1 million for one innovation. That's $1 million for the entire country that would be divvied up as far as requests that come in through this demonstration program. So why crowdsourcing? Well, when an agency is looking at how to improve their operations, crowdsourcing is a new source of data that can help with that process. It could help expand the geographic coverage or the resolution of the data that they would have available to them. It could also help reduce the information time lags for improved real-time situational awareness. It could reduce the dependence on and the cost associated with roadside sensors and systems and the maintenance of those. It could also help overcome some of the jurisdictional stovepipes that sometimes exist as crowdsourced data really transforms over the different jurisdictional areas. It doesn't really stop at boundaries like some of our actual in-field type of systems may. And it's a way to implement proactive operation strategies, and we'll talk some about that too. It's been proven in several areas to offer lower cost solutions that can improve safety and operation. So there's different types of crowdsourced data. The one that most people have heard of has been probe data that could be tracking of cell phones or other devices in a vehicle that would give speed and travel time. You also have event data that would detail when you might have crashes or stalled vehicles or potholes in the road or extreme rain or snow conditions out on the road system. Crowdsourced data could be travel behavior. It could tell when, where, how, what mode is used when people travel. You can mine social media data to be able to capture the sentiment the public has on road or agency performance. It could be vehicular in nature. Many of the vehicles these days have pretty extensive systems capturing a lot of information in those vehicles, things like braking, when the wipers are turned off, the temperature, and those could be transferred through devices out in the field, part of the infrastructure through what we would refer to as connected vehicles. And then finally, with mobile infrastructure and the Internet of Things, there's lots of other potential products that could transfer data. One example could be the typical orange cones that you see in work zones. could actually be smart cones, and they could be sharing location and surrounding speeds through those cones back to traffic management center. So the operations applications that are most commonly used have been traveler information and incident management as far as the use of crowdsourced data. But we're also starting to see expanding use across other application areas such as maintenance, road weather, and work zone. And in particular today, we'll talk about some of the traffic signal applications that can be used. So if you think about the way that a typical traffic operations center works, it relies on data that comes in. Data can come from many sources. It can come from service patrol vehicles. It can come from field devices. It can come from citizen calls. And now we see another source of data being crowdsourced information. And that crowdsourced information, as we talked about, can fill in geographical areas that were not covered before, or can fill in for latency issues that may exist within their data to be able to make that data more real time. So once that data comes into the traffic operations centers, then it's used in the applications that they work with, things like traveler information, incident management, freeway traffic management, arterial management, road weather management, and planned special events. So with that, that's kind of a briefing on the initiative of through the Everyday Counts. But let's go into our three presentations, and we'll start off with the first one from Jared Hall.
Thank you, Greg, for the introduction, and thank you all for having me. I'm excited to talk about our experience thus far in using crowdsourced data for signal timing operations. A little bit of overview about Austin. We maintain 1,012 traffic signals, 81 PHBs. Both of those numbers went up by 1 yesterday. We do all of our signal timing in-house. We have a staff of five signal engineers, and we have a pretty robust signal timing program. About 3 years ago, we started thinking that there is data that is available, there are technologies that are available that might could help us in our efforts in our signal timing. And we made a purchase of NRIX, and about a year after that made a purchase of Traction, and we've been using both, we've renewed both annually ever since then. So I'm going to give an overview of 4 cases where we have successfully demonstrated a benefit using the crowdsourced data. I'm going to go into each of these in a little bit of detail, but just to keep it short, I'm not going to dig too deep down into it, but I will be happy to answer any questions anybody has. The first thing I'll talk about is the prioritization of corridors that for our annual retiming program. So we have an official program where we retime 1/3 of our signals annually on a corridor level basis. The second application is the hotspot identification. So those are areas that we've identified that there's a signal timing issue that needs to be addressed. The third thing will be our MOEs and how we compute performance metrics of our retiming efforts. And then the fourth thing is what we have just started piloting recently, which is providing real-time travel time displays on DMS messages by using crowdsourced data, probe data. So the prioritization of retiming corridors, historically what we did was we would retime all of our corridors on a scheduled basis. So we retime 1/3 of all of our signals every year. And if it was retimed in 2016, it would get retimed again in 2020. And we thought that as Austin has grown a lot in the last few years, as development has sprung up in certain areas, more so than other areas, it makes a lot more sense for us to go and do a needs-based retiming. This is what we were finding is if we were doing it schedule-based, some areas would go retimed and we didn't need to make any changes. Some areas would retime in 1 year, and by the next year, there was already a lot of performance issues where we needed to look at it again. So what we started doing was we took INRIX data, we downloaded a large data set and put it into this tool that some researchers at University of Texas helped develop. And it can rank corridors based on the percentage of segments that have experienced a increase in travel time or a decrease in speed. So on this table, you can see that the number one corridor for the AM peak had a 95.93% of the segments on that corridor had a decrease in travel time, or I'm sorry, decrease in speed from when they were last retimed to the current time. And that is what elevated it, saying that it is the most needed corridor to be retimed. The second application, I was talking about the hotspot identification. So this isn't areas that are part of our official retiming program. These are things that are usually reported via citizens or something that we've observed or something that we've heard about, that there is a specific area, usually just one or two intersections, that have timing issues during a certain part of the day. Historically, what we would have to do is send out an engineer, make observations, decide what to do based on those observations, implement them, go back and look at them later. What we decided to do with our traction data is we can set up routes. So this specific location that I've shown is East Riverside Drive is a major corridor in southeast Austin. This Grove Boulevard is a relatively minor intersecting street. And during our PM peak, there was a lot of time provided for traffic on Grove Boulevard, but then as we got into sort of the shoulder of the peak into the evening, our timing plan reduced some of that time for Grove Boulevard and provided more for Riverside Drive. Cycle lengths got shorter. What we missed when we did our retiming was that at around 7 or 8 every night, there was a shift change at an industrial facility just south of here and a huge surge of traffic for about 30 minutes that was coming up and making that left turn movement. So rather than go out there, watch it for a day, put in some changes, and come back, watch it again, we set up this route and traction, and we're able to look on the left. You'll see here is the travel times over the time of day, and these are showing the horizontal axis here is time, and it starts around 4 p.m. and ends around 9 p.m. And you see these spikes that would kind of come often after 7, around 8 o'clock. We saw that that was happening and knew that there was an issue out there. So we made some timing changes and looked at the after data, and you see that those travel times lessened or flattened out a little bit after that peak. So we were able to make a quick adjustment without ever having to, I mean, we spot check it, but not having to devote 3 days to it. It doesn't necessarily make the fixes quicker, but it does allow one engineer to address multiple issues at once, since we don't actually have to have boots on the ground at that location. And the third thing is evaluating the benefits of our retiming efforts. So these are the MOEs. Our current MOEs, we look at travel time and a reliability index that's very similar to a buffer index. What we used to do is we would do even 4 years ago, we would do floating vehicle runs where we had a guy go up and truck up and down the corridor in a 99 Ford Explorer with a passenger who had a stopwatch and a clipboard and was just marking down times. And we realized that that was not really a representative sample of the number of users who were using that facility throughout the day. We would just do that in the peaks. We would do a couple of runs in each direction, and it depends on what day we go out there, and there's just so many variables that we may be missing. So this is a very simple calculation where you pull in average travel times and then average speeds, computing reliability indexes using the INRIX data for a larger percentage of the day to give us a much better idea of how effective our retiming efforts were. And then the last thing that I was going to go over is our traveler information system. This is something that we just began piloting this month. It's DMSs. We have about, I think about 10 or so DMSs that we're currently doing this on, where we're pulling Azure data via traction into our ATMS system, and then that's pushing data, pushing travel times out to the message boards. We provide 2 different types of information. One, just the travel time to a specific point, and then at diverge points in advance of a decision point providing travel times for those alternate routes. So this is just an example of what we've shown so far. The first one is travel times just to different intersecting streets, and the second option is providing a travel time to a certain location based on which street you choose. And that's all I had. I'll be happy to answer any questions towards the end, and I will turn it back over to Greg.
All right. Well, thanks, Jared. And as Jared mentioned, we're going to do the questions and answers at the end. So there is a pod that says questions and discussions. So if you have specific questions that you would like to ask any of the presenters, please put them in this discussion and question pod, and we'll get to those at the end of our presentation. And with that, now we'll move on to our second presentation, which will be Rahul and Tom from the Washington, D.C. area.
All right. Thank you, Greg.
Thank you, everyone.
So I'm Tom and Rahul, and we'll be discussing our use of probe data analytics through basically certain applications and certain projects we've done in the Washington, D.C. area. So I'll let Rahul here start with a little bit of an overview.
Hi, good afternoon, everyone. This is Rahul Jain, PTOE at Senior Transportation Engineer at District Department of Transportation. I'm accompanied by...
and I'm Tom Knopczynski, PE, and I work for Mead and Hunt, Sauber and Associates, which is a Mead and Hunt company. And we're a consultant. We work quite closely with DDOT for a lot of their traffic signal issues.
Starting with the agenda, we would focus on purpose and need, available data sources, DDOT projects where data is used, and future opportunities. So DDOT conducts several projects year-round for improving traffic safety and flow for pedestrians, vehicles, transit, and other multimodal alternatives of transportation. The main question is, how do we quantify benefits of projects and mitigations in a manner, in an efficient manner? So one way is to go out and observe the traffic flow and pedestrians, but that provides a limited snapshot of data, both in time and space. And it can be only one location for a limited amount of time. The other approach would be to collect data from a much wider area for a longer duration. So to handle these issues, DDOT went through its available sources of data and was able to use different sources depending on what was needed. Along the way, we have learned about some of the limitations of these data sets and charted a course forward. We are going to talk about the Vehicle Probe Project, the VPP software suite, which is part of the Regional Integrated Transportation Information System, or RITIS. The Vehicle Probe Project suite allows agencies to support operations, planning, analysis, research, and performance measure generation using probe data mixed with other agency transportation data. The suite consists of a collection of data, visualization, and retrieval tools. These web-based tools allow users to download reports, visualize data on maps or in other interactive graphics, and even download raw data for offline analysis. The I-95 Corridor Coalition, a consortium of state departments of transportation and metropolitan planning organizations, MPOs, along the I-95 corridor has been purchasing probe vehicle data, also known as vehicle probe project data from INRIX, HERE, and other commercial traffic data sources. So I would also, moving to the next slide for discussing practical applications. We mainly use Redis data for the DDOT citywide signal optimization project. The citywide traffic signal optimization program is focused on the central goals of making the District of Columbia traffic signals safer and friendlier for pedestrians and bicyclists, improving transit running time, and reducing traffic congestion as well as vehicular traffic emissions.
All right, so this project, of course, covers the whole city. We'll kind of be looking here at the largest section of the project, which is during the downtown, where we optimize the whole swath of downtown Washington, D.C. And it's a big project, over 600 signals in a tightly packed grid. We have more than 40 bus routes running through, 1,500 signalized crosswalks. You have cars, buses, peds, bikes, all interacting with each other on very busy roadways. So it's a huge project, and it's very hard to make signal timing adjustments without affecting large amounts of traffic one way or the other. And so we did this project, downloaded all the stuff, and we needed a way to quantify, what were the results? Did we see the improvements we expected? And the Redis suite was very helpful in being able to do it because of the huge amounts of data that it collects. So some of the things we collected included travel time data. Now, I mean, this is just saying like you can go out there and drive a car up and down the route and get a reasonable idea that the travel time is improved or what. But with the Redis suite, we get basically travel time all throughout the whole day. So whereas before we might only be driving in the AM and the PM, here we get it even at midnight or at other odd times of the day. And this result here for this particular stretch, the orange is before, the green is after. So after the signal timing, we can see, and especially with the red boxes during the AM, midday, and PM peaks, that we are seeing a drop in travel time here at this location at most times of the day, aggregated for an hour. One thing in particular that the VPP suite allows us to do because of the huge amount of data is to also see these results in terms of cumulative distribution plots. And here, the idea is it takes all of the travel times of all the cars, adds them up till you get to 100%, and you can sort of see the reliability of your route over time. So the idea is to have a more vertical line show up here. So most people are taking about the same amount of time to travel the route over the whole day. Red is before, green is after, and we can see here that when we collected the data afterwards, we sort of hit 100% around 12 minutes as opposed to before when it was at about 17 minutes. So a nice drop in travel time and a much more reliant travel time across the district. So of course these results can then be plotted on a map, and you can see how it goes across the whole area. Here green is improved travel time, blue is no change one way or the other, and red is a decrease. So we want to see lots of green and blue because it's so interconnected. You're going to have blue because they fight with each other, going east-west and going north-south. So this is a sort of an ideal when we're working with the signal timing to see this sort of travel time distribution. Finally, another option for displaying these results is a congestion scan, which takes a corridor, which is on the left here, is the length of the corridor, again, 12th Street from Massachusetts to the freeway, over the span of a day, and then it's a heat map indicating the speed as a percentage of free flow speed. So green means it's close to free flow, and then red is close to a stop. 12th Street is a route that is an inbound only route from the freeway. And so as we would expect with an inbound, we see a large amount of congestion in the before period, centering around 9 o'clock, so the morning rush. And it extended for quite some distance from about Pennsylvania Avenue to the south, and it extended from about 5 a.m. to almost lunchtime in certain areas. In the after, we were able to show that you still have a little bit of that congestion at the peak of the morning rush, but we definitely shortened both the distance a little bit and particularly the time that the congestion was experienced. But the nice thing about the probe data is that it isn't just large projects that it's useful for. It can be useful for very small projects as well. So we're going here a couple of examples of citizen requests. Citizen called in, the traffic is terrible on this corridor. We were able to go out there and make some quick timing changes. And at the end, we achieved a 2-minute travel time improvement over the mile corridor in the morning. But the nice thing about the Ritis suite and the data is that this is a very small project. You don't have either a lot of time or money to be able to collect large amounts of data. The data is already collected. You just have to go get it, and then you can map it out, and you can really show the difference to demonstrate the benefits that the changes made. Another use it has is being able to validate the citizen concerns. Much as what Jared mentioned in his presentation as well, a citizen can come in and say something's happened. In this particular incident, a particular Wednesday, the traffic got really bad all of a sudden. DDOT received a bunch of calls, and we went out there to try to figure out what was going on. But going out after the fact wasn't showing there to be much of an issue. However, when looking at the congestion scan, we saw that the citizen was correct. Something really did happen on that particular day. So this tells us something happened. What we found is there's sort of a limitation with the data. Is it doesn't necessarily tell us why or what happened, but it tells us something does happen. So then we know to start checking sources of what could have caused this. Could the signal have caused this? Was this a traffic incident? Was it a weird construction incident or a parking incident in DC? But it's helpful for being able to validate citizen requests without having to go out there multiple times with boots on the ground. This is a similar example. A change was made at a signal, and immediately afterwards, the citizens started making comments that the traffic got a lot worse. We were able to validate it, make some corrections, and then quickly show that the corrections were what needed to happen to bring the traffic back to normal. And finally, the data can also be used to calculate costs. In this example here, it's delay costs. And we have a comparison here between, for the same corridor, after some timing changes, the delay costs using both the PDA suite, the user delay cost tool that is found in the Ritis suite, as well as calculating it based on the synchro models of before and after. And the point is that they're not identical, and I should note the magnitude difference is due to the fact that synchro includes all of the side streets in its analysis, while the Ritis suite was only looking at the mainline traffic. So that's why the magnitude is different. But you notice the savings are on track in both these estimates. There's 20% savings in delay after the fact. What's particularly nice about the PDA suite here is that this is real data. It isn't just modeled estimated data. It's actual collected data. So we have that sort of confidence. And then one last example here, as opposed to being reactive, is an event where we were proactive and used the data beforehand to help mitigate the possibility of event as opposed to reacting to it afterwards. In this case, it was in 2015 when Pope Francis visited Washington, D.C. in September. DDOT tasked our company with coming up with first identifying what the impacts would be and coming up with mitigation for these impacts. And in particular, we needed to make estimates of what would happen if on a normal workday, lots of extra people came in and a lot of routes in downtown were closed, and so normal traffic operations weren't happening. And we needed to get this information out so that, news agencies could get the word out to the population, the federal government could make informed decisions on what to tell its employees to expect and to do on those days to sort of help mitigate the amounts of congestion we were expecting. So to do that, we used RITIS, INRIX, and other sources to sort of develop what are the typical congestion patterns in DC on a normal day. How far back does the congestion go on the major freeways entering into downtown? And then sort of identify where the additional road closures, what sort of new bottlenecks they were going to add. So for example, here we see Constitution Avenue was going to be closed. It has the little close symbol. And so the traffic coming in that would normally take Constitution would now probably be routing themselves onto this other ramp here, adding an additional congestion onto that ramp and creating a new bottleneck where a lot of normal traffic is now trying to go in a different direction. We were able to identify this stuff, and using both that data plus historical events, particularly unplanned events, and looking at the congestion they caused, we could make an estimate of the additional backups that the DC area would be seeing on its freeways as a result of the Pope's visit. In this case, on the major downtown freeway 395, an additional 8 miles of congestion. We were able to get this information to DDOT, who could then bring it over, brought it to the local news media, brought it to the federal government's attention, and they were able to get the word out. And so we got a lot of, particularly being the news, Pope-mageddon, traffic nightmares. The federal government told its employees basically pre-approved all telecommuting on the days that the Pope was here, so that any employee, if they wanted to, could choose to work from home instead of having to drive in. As well as developing traditional mitigation measures, detour routes, signage, signal timing changes. And the results were probably better than expected. Not only did Pope-mageddon and the 8-mile backup not occur, the traffic that day actually made it look like the DC Metro was a pleasant area to drive on a Monday morning rush. This here shows the Wednesday of the Pope's visit is the leftmost one, and then the 2 previous Wednesdays showing normal traffic. And there's a lot of green the day the Pope was here. Not only did Pope-mageddon not happen, the traffic was lighter than usual because of the way we were able to use the data to get the word out, and everyone was able to make timely adjustments to their schedule. And so now, having gone through a few examples, we'd like to go back to some of the things we've learned by using this data.
So moving on to the next slide on data quality, or how good is the data. So like any other data tool, we should know what's the source of the data and how it can vary over the given time period. So we are looking at the 2 slides, basically 2 different sets of data of the same location. One is from here.com and one is from inrix.com. But they show very different results due to the missing data values in the second set. In a nutshell, the next slide describes the phenomena that the probe data errored towards faster speeds, and the data collection process has improved over the time, which if used for long-term analysis can give an impression of worsening congestion when in fact it is actually the improvement of the quality of the probe data.
Yeah, so I mean essentially as the data gets better over time, in short-term analysis this change doesn't really impact, but over the long term you can see worsening congestion, but that's not necessarily what's happening, and it's just something to be aware of as the quality improves to be out. It's something that the I-95 corridor themselves have looked into and validated as being something that has happened over long term.
So the next item is like, where do we go from here regarding the applications of the Redis data? So the field data collection for travel time, which has been a common practice, will still be necessary, but the main application would be for validation purposes instead of the more traditional analytical or system.
The traditional methods would still use them mostly as to get a first impression or to sort of help to back check, what the data is showing. We can sort of look at it from a couple different directions. And so it's very helpful from an experience side, but we often need just more than what the traditional methods can provide.
And we will still use the location data from cell phones for vehicles and pedestrians, the transit AVL data, automated vehicle logger, AVL, for better understanding the differences between effects on buses versus effects on regular traffic. The capital bike share data could also show the bicycle-related origin and destination trends.
Yeah, so in the future, especially what we're looking for around here in Washington, D.C. is particularly more specific data for the different types of multimodal transportation options we have in the city. The probe data can show what's happening with the vehicles on the street, but that may not necessarily give us all the information we need in regards to buses. We have a lot more bicyclists and pedestrians, and sort of learning their origin and destinations could be helpful, or where Uber or Lyft data, again, showing particular routes that are or points of origin and destination. There's a lot of additional data out there that could really help, especially in these sort of complicated urban environments where there's a lot going on, and it's more than just the traffic, the vehicle traffic. And so that's everything we had, and thank you for listening. And as I said, we'll be able to answer questions at the end of the presentation, but right now we'd like to send it back over to Greg.
All right, thank you very much. Very informative presentation. Again, let me reiterate, we are collecting questions in the question and discussion pod, so we should have 15 to 20 minutes to address questions at the end of this webinar. So if you've got any questions for any of the presenters, please put them in the pod. With that, we will move over to Justin and his presentation from Lake County.
Thank you, Greg. Hello, everyone. I'll kind of just dive right into our application of crowdsourcing data. First, kind of some background. In Lake County, Lake County is one of the collar counties of the Chicago metropolitan area with a population of over 700,000 people. Lake County Passage is a model for the region incorporating communication between police dispatch centers, state and local agencies, real-time connection to traffic signals, cameras, and data collection sites, and providing traveler information to motorists in Lake County through various means. Our robust system includes a customized advanced transportation management system, over 400 closed-circuit television cameras installed for traffic monitoring only, connection to over 600 of the 750 traffic signals in the county, including state, county, and local jurisdictions, integrated portable changeable message signs, incident events through Waze and electronic communications with local police, and highway advisory radio. And all of this is managed in our Transportation Management Center from 6 a.m. to 7 p.m. Monday through Friday. And finally, we're also a member of the Travel Midwest group. So our communication methods for connecting to all of our traffic signals and ITS equipment include fiber interconnect, wireless radios, and cellular. Our traffic signal management tools consist of a cloud-based automated traffic signal performance measure system that is continuously collecting data 24/7, 365. 2 central traffic signal software systems where we can get the live status of a traffic signal and can upload and download the parameters of the traffic signal controller in a timely manner. Integration of traffic signals in our ATMS, which gives us the ability through center-to-center protocol to send certain commands to our traffic signals. An example would be sending a new coordination plan to a signal system for an event, either planned or unplanned. In the past, we had the ability to conduct signal coordination and timing studies through a yearly appropriation of funding, but have switched to a more proactive method of ETSPMs and crowdsourced travel time data. Before I get into crowdsourced travel times, there's some history on travel times in Lake County. We started using Bluetooth detectors at traffic signals, and we found the data was pretty accurate, but encountered drawbacks with the low hit rates, which are improving as time goes on, and also a delay in increasing or decreasing the posted travel times due to smoothing techniques and spacing of the detectors. And the biggest one, maintaining the equipment and paying for monthly subscriptions for storing the data. Then we wanted to switch to a crowdsourced data, and we were already pursuing an agreement with Waze for incident management, where we would share our confirmed incident data and construction information, and in return we would get unconfirmed event data from Waze. We found that we could also get travel times from Waze too, which fulfilled our travel time data needs. Our agreement went to our county board for approval, as all our agreements do, and they had no problem approving it. Then we started adding travel time routes in the Waze traffic tool. Each traffic tool is restricted to 200 routes, and we're able to get 4 traffic tools approved by Waze right away. We found that each traffic tool has a JSON feed that is updated approximately every 2 minutes, where we can get the data and store it. Initially, getting the data and storing was done in-house, where our TNC manager was able to create a program utilizing Python on a Linux virtual machine to store the Waze data in Postgres, which is a SQL database. He was able to generate travel time email alerts too when the current travel time was increased by 75% or higher when compared to the Waze historical travel time. And Waze also has documented view feed data specifications that go into more detail on understanding their traffic view feed data, along with a description of each JSON event. So one of the biggest questions we get is, why do you choose to continue with Waze? First, and probably the most obvious, is the data is free with our partnership. Anytime there is no-cost data sharing partnership is appealing to government agencies. We have another no-cost data sharing partnership we are pursuing in the connected vehicle environment too. The system requires very low maintenance because Waze owns and modifies the travel time algorithms to make them more accurate as time goes on. Usually travel times are only not available during updates, which usually only occur during the middle of the night. We have found the system is accurate from both a quantitative and qualitative standpoint. From a quantitative standpoint, we compared the data to Bluetooth data, which is the line chart to the right, where the red line is the Waze travel time and the blue line is the Bluetooth travel time. The typical travel time is the lower 10th percentile travel time during the study period, which is Tuesday through Thursday during the month of March. The bar chart below the line chart is the rounded travel time to the nearest minute that would be portrayed to the public. And the only reason I chose a bar chart was to show that the rounded travel times for both Waze and Bluetooth were the same. From a qualitative standpoint, we analyzed the congestion points for random Waze routes utilizing closed-circuit television cameras, along with displaying travel times on portable changeable message signs. With the CCTV cameras, when we got Waze travel time alerts, we pulled up the CCTV cameras to see if the backups that Waze was reporting were real or not. And they were always real. After the validations, we placed PCMS throughout the county and displayed the travel times. We picked locations throughout the county with the most variability in travel times. The goal is to see if the public thought the travel times were accurate. And over the entire 2019 summer, we served no concerns that we were displaying inaccurate travel times. And our experience in the past is if it was wrong, they would definitely let us know. For Waze storage, from about September 3rd, 2018 through February 6, 2020, we generated over 104 million rows of data with only 18 gigabytes of storage used, which is manageable for us. And the system is also still operating optimal for us. We use the crowdsourced Waze travel times in many different applications like our Advanced Transportation Management System, ETSPM, and our LCDOT project selection, which I'll get into later. For ATMS, we are logging the Waze travel times and have logic so we can use the travel times for website posting and PCMS with attribution to Waze. In our ATMS, we also have an alerting mechanism where we can create an account and get email notifications of events in areas of the county specified by the user. We're in the process of adding travel times into our email alerts where if a travel time goes above a certain threshold, it will generate an email to the users. Finally, we are in the process of a weather/travel time traffic signal responsive system, which I'll also get into later. In the screenshot on the screen, you can see what a snowstorm can do to travel times in the county. Typically, travel times are defaulted on in the layer options of our website, but we have chosen that if the number of travel times being posted are above a certain threshold, which we're still trying to calibrate what that threshold actually is, it will be defaulted off in the layer options because the website gets way too clustered during snow events. And we also want the users to be somewhat focused on the incidents because they tend to be the higher impact areas. Before we get into crowdsourced data inside of ETSPMs, I also wanted to give a brief background on ETSPMs, which was part of the Everyday Counts 4 initiative. ETSPMs consist of utilizing high-resolution data logging capabilities of modern traffic signal controllers that log items such as start of green indication, start of yellow indication, emergency preemption on, and so on, using about 109 event codes, which 146 reserved for future use. Each item is logged to the nearest tenth of a second. The data is then analyzed through a platform utilizing various research methodologies to generate performance measures to manage signal operations and maintenance to accomplish an agency's goals and objectives for safety and mobility. One example could be the Purdue Coordination Diagram, named after Purdue University, who led the effort. It basically plots vehicle arrivals against the current signal indication and reports how many vehicles arrive during the green indication, which can give insights on how good the coordination is for a given direction over a specified period of time. For our ETSPM system, we started with the open source software created by the Utah Department of Transportation, but decided to get a cloud-based system through a request for proposal process that would align better with the goals and objectives for Lake County. One of the important features we were seeking was integration of travel times from Waze. In the system requirements of our RFP, we made sure the system had the ability to log the travel times from our authorized API and be able to generate reports and charts. During this process, we reconfigured our Waze segments to make them more granulated for the coordinated traffic signal systems in the county, which is shown in the map to the right. It was important to align the Waze segments with our ATMS as well as our ETSPM system because they are interrelated. If there isn't a coordinated traffic signal system, then we space out our Waze segments in larger distances with breaking points at either bigger intersections or intersections where we would want to place PCMS boards. It's a process that needs to be well thought out at the beginning, but most likely will still need tweaking as time goes on. And finally, the integration wouldn't be complete until we got permission from Waze, especially with storing the data by a third party for Lake County's use. When we explained exactly what we were doing, They said we were not breaking any of the terms and conditions for our agreement. After we chose the TrafOp ETSPM system, they started creating our new corridor performance measure, which includes travel time index, planning time index, average travel time, congested time, which is the amount of time the travel time is increased by 75% or higher than the Waze historical travel time in the 2-minute increments that Waze provides us, and any other traffic signal performance data. The key is adding the crowdsourced data to ETSPM as the overlay of the existing traffic signal performance measures to get more of the story in diagnosing traffic signal operational issues, as no one piece of data will most likely tell the whole story. An example would be in the screenshot of our dashboard where we see elevated travel time index during the peak period, but when overlaid with vehicle delay from another performance measure, we can isolate the problem to 2 possible intersections that need further investigation. Another example could be split monitor, which shows if a phase or movement is gapping out, forcing off, or maxing out. If a phase is forcing off or maxing out a lot, it means the entire phase is being used, but could just be optimal phase duration, as most or all vehicles could be making it through during the green indication. However, the travel time and split failure performance measures will complete the story and tell the engineer if there are problems on the route that need to be fixed. An important process in the Chicago region for coordinated traffic signal timing is the signal coordination and timing process, in which turning movement counts are collected, a simulation traffic signal analysis is done, a before and after travel time study is done, coordination timings are implemented and calibrated, and a report is generated with the cost of benefit analysis. Typically, due to restrictions, this process is done by consultants. The data collection for SCAD process has switched from manually collected data from 1 to 2 days with people, could be interns, to 1 to 2 weeks of video data collection with more automation like Malvision, to the modern methodology of continuous data collection. Utilizing crowdsourced data in addition to the ETSPMs, we felt was the last piece of the puzzle for LCDOT to get the continuous data collection needed for the ability to do the SCAD process in-house rather than consulting it out. In doing the SCAD process in-house, we were able to pay for the entire ETSPM system over a 5-year contract period utilizing the money that was normally appropriated towards our yearly SCAD studies. And over the 5-year period, saving the county $17,300. We also have the ability to do SCAD studies more frequently due to the efficiencies. On the screen are annual benefits from 4 previous SCAD contracts with a benefit to cost ratio considering only the first year of annual benefit. And I am not saying that we will get the same benefit as the 4 contracts combined in 1 year. But in theory, combining corridors and multiple contracts into 1 year and doing them in-house would yield a higher annual benefit and higher benefit to cost ratio. We also have the ability to report on these improvements more frequently to our board members, which they use for their newsletters. And for other agencies in the Chicago region that want to add their traffic signals to our contract, is the approximate cost savings of $140,000 per year when compared to purchasing the system separately. Another way we are using crowdsourced data for improving traffic signal operations is during incident management, especially when a major roadway is closed due to a crash. For example, a crash that closed US 12 in both directions on December 18, 2019. In the chart on the screen, the blue line is the southbound travel time on the day of the crash, and the red line is the typical southbound travel time. The first vertical green line is the start of the full closure of US 12, which is a major route to Chicago with an ADT of about 32,800. The first time we saw Waze travel time spike, we immediately downloaded timing changes at the north end of the closure to account for the closure, and we saw the travel times immediately get better and more manageable. We continued to make timing changes at this intersection to manage the backups at the north end. And the only period of time when the travel time started to spike was when they opened one direction, in which we had to balance the new traffic coming. The second green line marks the end of the closure, in which both directions were open and traffic quickly went back to normal. Having the crowdsourced travel times in real time was critical in managing this incident. And ETSPMs are helpful, but can have an approximate delay of 25 minutes depending on the server strength and limitations of the traffic signal controller. So then the next question becomes, what happens when the police try to direct traffic instead of utilizing a traffic signal engineer, which we get to this graph. For the same incident, the chart here is the northbound direction of US 12 at the south end of the closure, where the police directed traffic against the traffic signal indications. As you can see, the travel time kept increasing as the closure went on, including after they opened the northbound direction. For most of the closure, the northbound travel time was about twice the travel time of the southbound direction, which was the direction we were managing. When the northbound direction opened, the travel times were still very high, which was unfortunate because it was the dominant direction of travel during the PM peak, which starts at around 4 p.m. Basically, people from Chicago are going home. One tool that we use to program projects is a project scoring matrix. This developed around the same time that the region was updating the surface transportation program process, and as our local council is developing its project methodology. Project-specific information such as crash rates, intersection level of service, non-motorized and transit components, regional significance, and project readiness are put into a matrix, scored, and ranked against each other. Other factors such as project cost and schedule are factored into the selection process as well, but the matrix has helped make the process more data-driven. This is a dynamic process which we update regularly as other tools or data become available, like ETSPMs and crowdsourced travel times. In 2020, we first introduced crowdsourced travel times into our project selection process. Since this is our first year, we developed a simplified methodology for testing our new process. We have a point system based on the increase of travel time when compared to the typical travel time, which could be any direction at any time of day. The typical travel time is based on the lower 10th percentile travel time over the analysis period, which is Tuesday through Thursday over a 1-month period of time. In the chart to the right, you can see one of the more dramatic examples where the percent increase in travel time, which is shown as the purple line, was over 70% and got the full 20-point value. We're also graphing the planning travel time to see if we wanted to use that in the future instead. Here is our uncompleted draft of our scoring matrix, but does include all of the travel time scoring. Our values range from 0 to 20, with a good distribution of values throughout all projects. Our goal was better project scoring separation through different components, and we feel that crowdsourced travel times gave that to us. We also feel the travel time scoring will be improved in the future when reporting from our ETSPM system improves, as we will be able to dive more into the data and get a better overall picture of operational deficiencies, which will give us the ability to generate new projects automatically instead of scoring existing projects, which are typically only generated by staff here at LCDOT. We are also using crowdsourced travel times to create weather or travel time responsive traffic signal systems. The theory is during bad weather, vehicle speeds are reduced, which constitutes an increase in travel time. The goal is to make coordination offset changes along traffic signals in the system to account for the reduction in vehicle speed. Our test corridor is going to be Deerfield Road and Deerfield and Highland Park, but this program is intended to be more widespread in the county. The alternate is manual timing changes by traffic signal engineers or retrofitting the entire county with adaptive systems, in which both are not feasible from either a time or economical standpoint. Also, during a snowstorm, we tend to be more concerned with incidents and broadcasting information to drivers rather than changing traffic signal timing countywide. In developing a travel time responsive system, we are integrating our Waze travel times, our ATMS, central signal system software, and ETSPM. To the right is the flow chart of how we want the interaction to take place. We know there are a lot of moving parts, and our proposed flow is going to be the travel times come into the ATMS and are analyzed. If the travel time is above a certain user-defined threshold, it will generate an event in our ATMS. The operator will have the ability to accept or reject the event based on the conditions, meaning what is causing the increased travel time. Obviously, incidents are a totally different scenario. If accepted, the ATMS will send a command to our central traffic signal software to run different coordination patterns for the signal system. When the event is ended, the signal times will automatically go back to normal. Then, in the days or weeks after the event is complete, the signal engineer will analyze the situation in our ETSPM system to see if the coordination patterns need calibration before the next storm. Now that we have a better understanding of our methodology for creating Waze travel time routes, we hope to get this operational before the 2020-2021 winter season, or our next winter season. You can also probably imagine how this methodology could grow into other applications with a robust ATMS, including incidents and more. And that is all that I have. Thanks for listening, and back to you, Greg.
Okay, well, thank you, Justin, and a special thanks for giving a shout out to EDC4. You used one of the initiatives from that as well, and that reminds me just to bring up the fact that our Everyday Counts initiatives are a 2-year initiative, and right now we are in the 2nd year of the EDC5. So in next year, in 2021, there'll be EDC6 and a whole new group of initiatives will be coming out from that. So that's something to look forward to next year. But anyway, so if we could, Nilo, if we could get up the question that we have and the poll for that. What we'd like to do is use the crowdsourcing principles to engage the collective knowledge of the audience to help us prepare for some upcoming webinars. And so the question we have for you is, what topics would you like to see in future installments of the Adventures in Crowdsourcing webinar series? And as we mentioned, this is the 5th one, so let me go back and just reiterate the 4 items that we have had in our previous webinars. The first one was on engaging navigation providers. The second was on data management and governance. The third was on incident management tools. And the fourth was on vendor engagement, or how to engage crowdsource vendors. So, and then this 5th one was on traffic signal applications. So what I would ask for you is, if you can, into the poll box there, please type in anything that you would like to see as far as future webinars. And I'll give you a few minutes to do that. And I'll also just point out that if you have any other questions for our presenters, we'll get to that next. And so you could use the question and discussion chat pod to add those questions in there. So I'll give you a few minutes, and then we'll move to the question and answer session here. Okay, very good. So we got 7 suggestions. We will certainly take a look at those and consider those. And I'll ask Nilo if you will leave this up for a little bit as we move into the question and answer portion. If you have any other things come to mind that you'd want to put in here as a suggestion, we certainly appreciate that. And with that, we'll start out question and answers with the first one would be for Jared. And the question is, Jared, did you ever consider adaptive traffic solutions?
The answer is yes, we have considered it. We've actually piloted an adaptive solution on 3 corridors over the last few years. They were met with mixed results. We did demonstrate a better travel time overall, but some of the issues we were having, we had very unreliable detection. For adaptive to work really well, it needs really good working detection in each direction. We had issues we were running an older controller software at the time that wasn't always taking the commands properly from our ATMS system. And the corridors that we used, we sort of came to the conclusion that they were very predictable. They were commuter corridors that a good signal engineer could go in and with a pretty good degree of certainty predict what travel patterns will look like on a given day. So we're really only seeing improvements on those incidents and times that were unanticipated. We do have a few traffic responsive systems that we put out, which are we're a little bit more comfortable with, just because it's usually a single detector or just 2 or 3 detectors that we have to make sure that we maintain. And those would be scenarios when if we could ever expect a surge in a single direction or 2 different directions, then it would kick the controllers into a pre-timed plan that we've set that would allow for that greater capacity. So our conclusion on adaptive is that we might look at it again in the future. We don't have any immediate plans to, but we do, or we are experiencing some positive experiences with our traffic responsive, and we'll probably roll a few more of those out.
All right, thank you, Jared. And while you're up, we'll go to the second question for you. What ATMS are you using?
Our ATMS is KITS from Kinley Horn.
All right, thank you. Next for Rahul, the question is, aren't most signals in Washington, D.C. pre-timed, especially in downtown?
Yes. Pretty much the vast majority of signals actually throughout most of the city are pre-timed. And in fact, sort of relating to the next question there about pedestrian and cycle detection, I mean, we have some pedestrian, standard push button detection, almost no cycle detection. When we use bicycle signals, they come in pre-timed, essentially. A lot of them are in the downtown. Pedestrians in general have an expectation of not having to push the button, and where we have, say, hawk signals and stuff, we find that there's a lot of confusion on the expectation of what the detection is supposed to be doing. And so generally, if we look to pre-time or at least set to ped recall every signal, because that's what most of the citizens are expecting when they're traveling around in DC. Okay.
So you mentioned the Pope's visit as an example. Question is, would that be applicable for something like a presidential inauguration, or one that I might add, a World Series championship parade?
Yes. In fact, for the Pope's visit, amongst the data we used was the presidential inauguration, just to sort of get an an idea of the kind of traffic incidents we'd have within the city. So yeah, it's applicable in those situations as well. The only slight difference is the presidential inauguration is, I would say, I guess describe it a little more expected in that the federal government is a lot more proactive about it because it's sort of their deal. So, but yeah, it's definitely a similar situation and a big day at DDOT trying to mitigate the traffic headaches it causes.
All right, thank you. And then the next question, well, actually, next two I think we kind of combined for Tom and Rahul would be, did you use any real data, which I assume is talking about sensor data from the traffic signaling systems? And in particular, since some of the probe data has relatively low penetration levels, was there any, I guess, was there any validation or integration of that sensor data with the probe data?
By and large, our sensor data is not, the system in DC is not particularly reliable, at least from a coverage standpoint. It's hard to keep them maintained within the city. Most of the sensors that we have are mostly on the freeways rather than in the on the surface streets, which is what the optimization was focusing on in particular. So other than, you know, the sort of the traditional free-floating cars in the stream, we didn't have a lot of traffic signal data to go on. It was just the free-floating car data, which sort of went back and validated. And you know, as we described, we look at the multiple sources of data, and we don't necessarily combine them when we're looking at them. We look at them separately and see what sort of differences they're coming up with as well, to you know, kind of cross-validate between the different sources, particularly like here in INRIX. They often show similar but slightly different things, and it's helpful looking at them separately to sort of make decisions on what the actual results are.
All right, thank you. So our next question is for Justin, and it does look like this question came in before you touched on this in the presentation, but the question was, what cloud-based ETSPM system are you using, and what led you to choose that system? I know you kind of touched on that. Is there anything that you'd like to add to that, Justin?
Yeah, I can add a little bit. Through our RFP process, I created over 250 system requirements, most were with referencing the high-resolution data logging enumerations. But we selected 3 people to interview, and based on those interviews, we just went with the system that checked the most boxes for us, and I was able to accomplish our goals and objectives in a really nice, timely manner.
All right, thank you. So with that gets us to the end of the questions. I know the last thing on here was another suggestion for our webinar series, so Gail will make sure and get that added to the list for the webinar series. I don't see any other questions coming in. And we're getting towards the end of our time as it is. So I'd like to just say I'd like to personally thank each of the presenters today. Jared, we appreciate you showing how Austin was able to use your data and shift towards performance-based retiming. And Rahul and Tom, thanks for showing how you use data through the RITIS Probe Data Analytics Suite to verify your signalization improvements, and then Justin, how you use the Waze data to significantly save costs and real-time enhancements to the signal system as well for your traveler information. Thanks to everyone who attended the webinar. We hope you were able to learn something today that you can take and share with your agency and improve your traffic signal operations. We look to meet with you again, hopefully in April, as we have a webinar on back of the queue for freeway applications for mitigating secondary crashes. And then I'll just point out, we have a slide showing now the operations leaders for this initiative in federal highways would be James Collier and Paul Joden. So particularly if you had questions about some of the resources that we have available, those would be the people that I would suggest to get in touch with, and you know, they can certainly answer your questions. Also, you know, just point out that these webinars are recorded and that they'll be available on the National Operations Center of Excellence website. I think this one is probably next week, I think is what Nilo was saying. So certainly would recommend that if you have others that may have an interest in this information they weren't able to attend today, that's a way that they can take a look at this webinar. So many thanks to everybody, and we'll see you at the next one.